love our roads. We love them so much that we seem determined to pave the entire world. But maybe roads can become the future of renewable energy. That's right, roads as energy generators. How? By building them with solar panels. Do we have the technology? Could we power the entire world? And what are the drawbacks? This is What If, and here's what would happen if we paved our roads with solar panels. In 2017, the United Kingdom promised to run on 100% renewable energy by 2025. Yet, they still have a long way to go, with only 33% of their energy having come from renewable sources in 2018. Could solar panel roads be the answer? Energy is created when photons from the sun hit a silicon solar panel. Silicon is a semiconductor and has similar properties to metal and an electrical insulator. So, when the sun's photons hit the silicon atoms in a solar cell, they transfer their energy to loose electrons, which knocks them off the silicon atoms. This generates electricity. Since the year 2000, there has been a 200% increase in global renewable energy consumption. Sounds good for the solar industry. However, in 2019, of the 17,000 terawatt hours of renewable energy created globally, only 3% came from solar. Turning our abundance of roads into energy-creating thoroughfares could move solar to the fast lane for renewable sources. But how much solar road would we need? Well, in 2016, Waywatt built a 1-kilometer solar roadway. It generated about 280 megawatt hours per year. That's enough energy to power 25 homes for 12 months. The United Kingdom has around 400,000 kilometers of road. If just 20% of those roads were converted, that would equal around 81,000 kilometers of new solar panel paved roads. The energy from those roads would only account for 5% of the UK's total energy consumption in a year. And the price tag? Well, a 1-kilometer road in Normandy, France cost €5 million, or approximately $5.5 million to build. And that's enough to burn a sizable hole in a city's wallet. So let's hope the cost for solar technology goes down before attempting to build an 81,000-kilometer stretch. How would solar roadways change the world, though? The largest change, and the reason behind creating these solar roads, is the reduction of carbon dioxide, the biggest driver of global climate change. Many roads are currently paved in asphalt. This material absorbs 80 to 95% of the sun's rays, which increases heat on the road and surrounding areas, a phenomenon called the urban heat island effect. Switching over to solar roads would reduce this effect, creating cooler roadways and cooler cities. As these solar roads stretched over more of the globe, the coal industry would have to shutter its doors, and we would need less petroleum for asphalt production. Many people would lose their jobs. Governments would need to create programs to retool the workers for the growing demand of solar road construction. Then there's the roads themselves. To build these roads, solar panels are placed between layers of glass, silicon, rubber, and concrete. This makes for a slippery road, especially during rain or snow. The roads would need a durable coating to create traction, and that coating would have to be safe for the environment and humans. Or would we develop improved car tires from another material to better grip road surfaces? Another route is to create smart solar roads. These roads would include technology to keep their surface above freezing, charge electric cars as they drive, and use LEDs for bright road surface markings. There are a lot of roadblocks for this new technology, cost, material, and safety being the big ones. But is it worth it to invest in research and development? In 2014, the Netherlands built a solar bike path. This 70-meter bike path generated 3,000 kilowatt hours. In other words, the solar bike path could power a small household for 1 year. Talk about recycling your carbon footprint in a powerful way. Despite current limitations, solar paved roads might still be a possibility in our future. That's a story for another What If.
Hi everyone, I am Dr. A.R. Vijay Babu, working as an assistant professor in Department of EEE, Vignan's Foundation for Science, Technology and Research, deemed to be Universe. So, we are dealing with the subject Spvt 2, that is Solar Photovoltaic Technologies 2. So, in this, we have already gone through unit number 1 and unit number 2. This unit number 1 consists of design aspects of PV cells, and unit number 2 consists of solar PV modules. Now, let's start our unit number 3, that is maximum power point tracking. So coming to the syllabus of this unit, we are going to learn about tracking. The tracking is of two types. One is electrical tracking and mechanical tracking. So we are going to see what is sun tracking, what is a single axis and dual axis tracking, and this complete thing is a mechanical tracking systems that we are going to discuss later in this unit. Initially, we are going to start with the electrical tracking. We are going to see what are PV curves, what is a maximum voltage, what is a maximum current in a PV cell, and what is the concept of Mppt techniques, and we'll also go through some introduction to some 6 algorithms in this particular subject. So coming to the learning objectives of this unit, we are going to see the operating point of IV characteristics, and then we are going to see what is the concept of maximum power point technique. Then we are going to see what is power interface, which is a very important component in the maximum power point tracking system. And then we are going to see what is the need of maximum power point tracking, and then we will see introduction to some MPPT algorithms. And we are going to see altogether 6 algorithms in this particular lecture. The first one is the fixed voltage algorithm, second one is the fractional open circuit voltage algorithm, third one is the pilot cell algorithm, fourth one is the fractional short circuit current algorithm, fifth one is the perturb and observe algorithm, and the last one is the incremental conductance algorithm. And all these 6 concepts deals with the electrical tracking. Now at the end we will see the 7th topic, that is the mechanical tracking, that is what is a sun tracker, what is a single axis tracker, and what is a dual axis tracker. So before going into the topic, let's briefly discuss the 3 important parameters of a solar cell. They are short circuit current, open circuit voltage, and maximum power, which we have already gone through them in our previous lectures, but again we'll go through them in order to have the clear understanding about the topic which we are going to present later in this video. Right? The first one is a short circuit current. So what is a short circuit current? The short circuit current is the maximum current that is drawn by the PV cell. The voltage across the PV cell is 0. That is, the short circuit current is equal to the maximum current. You can see it here when the voltage across the solar cell is 0. So this short circuit current is a light generated current, and it is proportional to the solar radiation intensity, as you can see in the figure over there. And this point is called the short circuit current, or the maximum current that is drawn from a PV cell when the voltage across the PV cell is 0. Now the second parameter is the open circuit voltage. What is this open circuit voltage? The open circuit voltage is the maximum voltage generated by a solar cell at a given light intensity. The open circuit voltage is also the voltage at which the current flowing through the cell is 0. That is, the open circuit voltage is equivalent to the maximum voltage, that is when I equal to 0. This open circuit voltage increases with increase in light intensity. Right, as you can see here, and the point which is on the x-axis, on which the current is equal to 0, is called the open circuit voltage, which is the maximum voltage that is generated across a PV cell. Now, the third important parameter of a PV cell is peak power or peak operating point or maximum operating point. So you can see here, so far we have seen the IV curve of a solar cell, and we can also draw the PV curve of a solar cell, which is derived from the IV curve of a solar cell, and the peak point of this IV curve is called the peak power that is generated by the PV cell. Now, the voltage which is corresponding to that maximum power point is called the voltage at maximum power point or maximum voltage, and the current which is corresponding to that peak power is known as the peak current or maximum current, or the current corresponding to the peak power point. Right? So, the load which is connected across a PV panel should always operate the PV cell at maximum power point in order to get the maximum benefit from a solar cell. That is, in order to deliver the maximum energy to the load, the solar panel have to be always operate at maximum power point. Now, let's enter into our actual topic, that is concept of MPPT. So, the concept of operating the solar panel at maximum power point always is called a maximum power point tracking, right? So we need to track the maximum power always in such a way that it is giving maximum power to the load, and the process of tracking this solar panel is called a maximum power point. See, let's see the figure here. In the figure, you can clearly see there is a solar panel which is connected to the load, and the voltage which is generated by this solar panel is V, and the current through the solar panel is I, and R0 is the load resistance to which the solar panel has to supply, and the value of R0 will vary from 0 to infinite. So when R0 is 0, it is nothing but a short circuit. When R0 is infinity, it is nothing but a open circuit. So the load will vary from short circuit to the open circuit when solar panel is connected across its terminals. Now, what is a operating point? The point of intersection of the IV curve of a solar cell with the load line is called the operating point of a solar cell. You can clearly see in the picture over there. You can see there is a IV curve of a solar cell and there is a load line, and the point where this load line is intersecting the IV curve of a solar cell, and that point we call it a operating point. Here you can clearly see the slope of this load line is delta I by delta V. Right? So what is I by V? It is G, that is conductance. And what is conductance? Inverse of resistance. That is, the slope of the load line is 1 by R0. Right? So the load which is connected across a PV cell can be varied from R0 is equal to 0, that is open circuit, to R0 is equal to infinity, that is short circuit. So let's see the case when R0 is equal to infinite, that is open circuit. Right, R0 equal to infinite, that is open circuit. So the slope of this load line is delta I by delta V, which is given by 1 by R0. So when R0 is infinite, then the slope is given by 1 by R0, that is 1 by infinite. That is 1 by infinite value will be 0, that is open circuit. So whenever the load resistance R0 is infinite, the slope is 0, and the operating point aligns itself along the x-axis. The operating point aligns itself along the x-axis. The corresponding point on the x-axis where this load line is aligned itself is called the open circuit voltage. Now let us see, when R0 is infinite, then slope is equal to 1 by R0. So R0 is infinity, so slope is equal to 1 by R0, so that is 1 by infinite, and the value will be 0. So when the slope is 0, the load line aligns itself along the x-axis, and the point is called the open circuit voltage, and the corresponding point is called the open circuit voltage. That is, whenever the resistance is infinity, the load line is aligned along the x-axis, and the corresponding point is called the open circuit voltage, as you can see in the figure clearly. And when R0 is 0, that is a short circuit, then what is the slope? Slope is given by 1 by R0. So 1 by R0 is 0. So 1 by 0 will be infinite. That is, whenever the load resistance is 0, then the slope is infinite, and the operating point shifts along the y-axis. The corresponding point is called the short circuit current, ISC. As you can see in the figure over there, the load line is aligned across the y-axis, that is called the current axis, and the point where this load line aligned is called the short circuit current. Whenever the load resistance is infinite, the slope of the load line is 0. Then the operating point shifts and aligns along the x-axis. Now consider a modified figure where the operating point represents the maximum power point. Right? Now RT is the terminal resistance seen across the terminals viewed from the PV panel. What is the slope of the load line now? Previously the slope of the load line is 1 by R0. Now since we are focusing on RT, which is the terminal resistance, now the slope of the load line is 1 by RT. 1 by RT. Now RT is the terminal resistance which corresponds to the maximum power point of a PV module. That is, as you can see here, RT is equivalent to Vm by Im. That is what is Vm? The voltage at maximum power, and what is Im? The current at maximum power. So what is RT? RT is the resistance corresponding to the maximum power point, which is the ratio of voltage at maximum power to the current at maximum power. See, now the point of intersection of this PV curve with the load line, that is 1 by RT line, is called the operating point A, as indicated in the figure, which corresponds to maximum power point of the PV module. Right? Where Mppt or Pm or Pma is the maximum power point or peak operating point. The voltage which corresponds to this maximum power point is called the maximum voltage, and the current which corresponds to this maximum power point is called the maximum current. And you can see Pm is the multiplication of or the Pm or Pma, that is the maximum power at operating point. A is the product of V and Vm and Im. Now you can see here, now I have an operating point at point A. Because of the increase in radiation or increase in temperature, the point may shift either to right side or to left side. Now let us see whether the operating point moved either to right side or to left side. What is the power drawn by this that new operating points? Now first let us see if the load line is shifted to from the actual operating point A, which corresponds to the maximum power point, to the operating point B, as shown in the figure. Now the operating point A is shifted to operating point B, that is the operating point A is shifted towards the right and came to a point B. due to some reason, maybe because of temperature change or irradiation change. Now let us see what is the value of the power drawn from the PV module. So whenever the operating point shifts from A to B towards the right of the actual operating point A, this means that now you can see clearly that the slope of the load line is decreased. So whenever the slope of the load line is decreased, that means 1 by RT is decreased, which means whenever 1 by RT is decreased, which is nothing but RT is increased, that is the terminal resistance is increased. So whenever the terminal resistance increases, then the load resistance also increases. So this might be the probable reason. That is, so whenever the operating point A shifts right to the operating point B, then the slope of the load line is reduced. So whenever the slope of the load line, that is 1 by RT, is reduced, then automatically the value of RT is increased, and this leads to the increase in the R0. And you can clearly see in the figure that the point B is the new operating point, and the power which corresponds to this new operating point B is PMB, that is the maximum power corresponding to the operating point B. And V and I are the voltage and current which corresponds to the operating point B. Now the peak power at operating point B is given by PMB, which is the product of V and I, which is far away from the actual operating point A. So we can clearly see that PMB is less than the PMA, that is the maximum power will always be attained at PMA. Previously we have shifted the load line to right side. Now let's shift the load line to left side to the point C from the operating point A, which corresponds to the maximum power point. This means the slope of the load line is increased, which means the 1 by RT is increased, and thereby the value of RT is decreased. So whenever the value of RT is decreased, this leads to the decrease in the value of load resistance R0. And here also, now PMC, which you can see in the figure, is the maximum power at operating point C, and V and I are the corresponding voltage and current at this operating point C. And you can also clearly see that the PMC is also far away from the actual operating point A, which corresponds to maximum power, and thereby PMC is also less than PMA. So what can we conclude from this? We will get the maximum power from the solar photovoltaic panel only when it is aligned at an operating point A. At point A itself only we will get the maximum power from a solar panel. If it shifts to right or to the left, you will never get the maximum power, and the power which you will get will be less than the maximum power at operating point A. And that is the reason why we got PMB is less than PMA, as well as PMC is less than PMA. So from the discussion we came to know that the PV module draws the peak power only at the operating point A. Therefore, we should somehow operate the PV panel at around A always in order to draw maximum power from the PV module. So, our intention is to operate the PV panel always at the point A in order to obtain the maximum power. Now, the discussion is, what if the load that is connected across the PV panel changes? So far we have keep in mind that R0 is constant. Now if R0 keeps on changing, then what is the fate of this maximum power point? That is what a question here. If R0 changes, so let's assume that the value of the load resistance R0 changes. If R0 changes, then automatically RT also changes, and the corresponding operating point shifts either to the right or to the left of the peak power drawn from the PV module is less. If R0 changes, then obviously RT also will change. So whenever the RT changes, the load line will move either to right or to left from the actual point A. And this leads to the decrease in the maximum power drawn from the PV panel. So in order to keep the value of the terminal resistance RT constant, irrespective of the change in the value of the R0, we have to introduce a block in between the PV panel and the load. That is power interface with controller input. Right. So now we are inserting the power interface with control input in between the PV panel as well as the load resistance in order to keep the value of the power drawn from the PV panel is constant by keeping the value of RT constant, whatever may be the change in the value of load resistance or not. So the function of the power interface with control input is to maintain the input impedance of the power interface block, that is RT constant, irrespective of the changes in the value of load resistance or not. That is, even if R0 changes, the control input has to adjust itself in order to maintain the value of the input resistance constant. So that is the function of this power interface with the control input block, which is kept in between the solar panel and the load. Whenever the load changes, then the control input should be adjusted in such a way that the input impedance of the power interface, that is the terminal resistance RT, should be kept constant in order to draw the maximum power from the PV panel. So the input impedance R0 should be regulated in order to obtain the maximum power from the PV panel. So whatever may be the value of R0, the control input should accordingly change such that the input impedance of the power interface block, that is the terminal resistance RT, is made constant. In such a case, the terminal resistance as seen from the PV module is always fixed or constant irrespective of the changes in the value of the load resistance or not, and maintains the operating point always at A, such that peak power is always drawn from the PV module, and this process is known as maximum power point tracking. So the concept of Mppt is crucial in order to utilize the PV panel to the fullest.